Welcome to the second lecture of this crash course in metric geometry. So, we'll start with recalling something from the previous lecture. So, just let T be a metric space and recall let gamma AB to X be a rectifiable curve. It means that the length of gamma is finite. Then uh, there exists a unique map. So basically, I'm recalling the arc length parameterization of the variable curve 0 to LD of gamma. Is that uh, gamma is basically gamma's composition S, where S is the arc length function. Where S of T is basically LD of gamma restricted over A to T. Okay. So I will mention some results regarding the properties of this arc length parameterization. So which I will use later. So the first one is so just 2.1 is just to make sure that lecture 2 result once. In that sense, for every u belonging to this interval, we have u is equals to basically length of gamma s restricted to 0 to u. This is fairly easy to prove. We just need to use the definition. So basically, let u belongs to this interval LD of gamma, and let T belongs to this interval AB, such that LD of the length of gamma from A to T is nothing but U. Okay, so like this is nothing but S of T is equals to U. Okay, this one, so S of T is equals to U. So anyway, by the construction we have, so gamma restricted over A to T is nothing but gamma S restricted over 0 to U from position S restricted over A to T. Okay, so recall the proof of this fact that there exists arc length parameterization, and then the way we constructed this will follow from that one. So let us just, for the convenience, let us say this one as gamma t, and this one as gamma su, and this one as st. Okay, so basically what we're getting is that the path gamma t is obtained by the sorry so the gamma t is obtained by the curve gamma SU by the change of parameter ST. Okay, and by the invariance of length, what we have, so LD of gamma T is nothing but this length of gamma SU. And what is this? So LD of gamma T is what? This is U. This implies U is equals to LD of gamma, this gamma is restricted over 0 to U. So that's what we wanted to prove. So it means that for the arc length parameterization of a rectifiable curve, the length, so you restrict U, so you fix any U in this interval, okay, in this interval, and basically take the length of this gamma S. This is going to give you this U. Okay. So so for a general curve, we are making a definition which I will call as curve
So is the
parameter.
gamma is kind of geodesic? Can we think of gamma as
Yeah,
a
yeah.
geodesic?
Hello.
Yeah, can you hear me?
Yeah, yeah.
Yeah,
No.
I'm saying,
Yeah.
can you? Okay.
Mm-hmm.
Yeah, I'm saying, is it this gamma is kind of geodesic or something else?
No, not a geodesic here at
Okay.
present. For that one, it has to be isometry and like between any
Right,
two
right.
points, it has
Okay,
to
it could
satisfy.
be in schema. Right.
Yeah.
Okay.
So, so okay. So the definition is this is curve.
Can you share again the screen? It is not visible for me
Oh,
at
screen is
least.
not visible. Just let me see.
Yeah, the screen is not visible.
Wait a minute. Yeah, is it fine now? Is
Yeah.
it visible? Yeah. Okay. So curve parameterized by arc length. Okay. So we say that rectifiable curve AV to X is uh, is parameterized by arc length if for all U and V satisfying we have V minus U is basically nothing but LD of gamma U comma V. Okay. So we have any curve in a metric space, we will say that it is actually parameterized by arc length if that curve satisfies this property. It will be fairly easy to see that the arc length parameterization of a curve satisfies this property. Okay? This gamma S. So in particular, if a curve is parameterized by arc length, it satisfies Basically, the length of the curve is nothing but. Okay. Okay, so here one more observation is there. Once a curve is already parameterized by arc length, since it satisfies this definition, then this function st, this is basically going to be strictly increasing. Okay, not just increasing. This is going to be strictly increasing. So okay, so I will write it in an exercise only. So so that the curve, basically the curve gamma s, which I told earlier, of gamma x is parameterized by arc length. Okay, fine. So
Yeah. So assume if gamma is C1, then is it the same as mod gamma prime equal to 1? The definition of this
if yeah, what
parameter.
if
If the
gamma is
gamma prime is always 1, mod gamma prime, is
huh?
it same as curve parameterized by arc length? Because I'm thinking of if it is like integral over a to b gamma prime dt. So if
Yeah, yeah.
mod gamma prime is 1, okay. So it is same, right? If and only if gamma is
Y-
just C1.
Yeah, yeah. Means once you have a length formula in the sense of like
Uh-huh.
in
Okay.
like gamma dot t, norm of gamma dot t dt integral.
Yeah.
So in
Mhm.
that case, if you have this property for any v comma u, v minus u is basically this one.
Right.
Okay, so
Okay.
you are
Then
saying
you will
that for
get
that
gamma
curve,
prime.
this will okay. So for that curve, this will always hold. You're saying
Yeah, yeah. Yes. Yeah, if mod gamma prime is 1.
okay, yeah. If mod gamma prime is one, yeah. No, but even if mod gamma
Mm-hmm.
prime is one, like
Mm-hmm.
how do you show this one that for any u v will satisfy this one?
Okay, so length of gamma means from u to b means integral from u to b gamma
Mhm.
prime dt, right? So if mod gamma prime is 1, then it is
Okay, it
basically
is
b
throughout
minus.
one.
Yeah.
Okay, it
Yeah,
is
yeah.
throughout one.
Means it
Okay,
is gamma prime is always 1. Yeah.
okay, okay, okay. Fine, fine. Yeah,
It's mod of this. Yeah.
yeah,
Yeah,
exactly,
but it
exactly.
is like more general because here we don't assuming gamma is C1. We are
Yeah,
not
exactly.
assuming gamma is
So
okay.
it is kind of saying that we have parameterized a curve by the unit speed.
Okay. Yeah, right.
Like unit speed means gamma prime t equals to one.
Mhm. Okay.
Okay, so now we will talk about normal metric. So okay, so from now onwards, I'm going to take a rectifiably connected metric space. So let x comma d be a rectifiably connected metric space, and rho is from x to d. Uh, let us say anyway. Let us say Borel measurable only. Ultimately, we are going to come down to like rho is continuous and positive, but just to define, writing this one. So we define the row length row length of rectifiable curve gamma gamma subset e comma b to x. So recall the line integral. In that way only we are going to define by. So let us denote L rho of gamma is nothing but rho ds. So this ds is nothing but the arc length parameter for that metric space. Okay. So for the Euclidean space, ds is nothing but mod dz. Okay. Okay. So just a notation, and now here is the definition. So a to b rho of gamma t. Oh, sorry. Is 0 to LD. So we're taking the arc length parameterization of this curve gamma, and we're doing this one. Okay. And this is going to be the rho of gamma t. Okay. So basically this row determines distance distance function on x. Okay. So I think that that is clear how to define. So d rho of x comma y, okay, is nothing but the infimum over gamma L rho of gamma, such that gamma is a rectifiable curve joining x and y. Okay, so I hope this definition is clear. So but what we are doing is we are taking 2 points x and y, and we are taking the all rectifiable curves joining x and y. We are taking the L rho of gamma, means row length of those curves, and taking the infimum of the curve. Okay. Yeah. So in general, this may not be a metric space. General x d rho need not be metric space. I mean, if this row is 0 at some point, then that will create a problem. And if so, yeah. So here it is. If x d rho is a metric space, x d rho is a metric space, then we call such row metric density.
Can you give some examples so that it is not metric
Yeah, yeah,
space in general? Okay.
yeah. I will. Yeah, that will come in example section. Example and non-examples. I will just come to that.
Okay.
Okay, so we call such row. So a row which gives this as a metric space, they are known as a metric density. We call them as a metric density. So, however, however, if row is positive and continuous, then x d row is always a metric space. So, oh, this will be a nice exercise to do it. But I will prove this. So one part of this I will prove in like I will sort of prove in the later section. Uh, once we are talking about the once we'll talk about the inner metric. So the thing is, now if rho is positive and continuous, then this is always going to be a metric space. Okay. So if you want to find a row so that this D row will not be a metric space, one thing would be to uh, uh, yeah. So if yeah, so what would be idea to do is that you take a row which is zero, which is not positive. I mean, which takes the value zero. So for x is not equals to y, we need this D row x comma y is equals to zero. Okay, so it is like I mean this can be done, isn't it? Like if you take
Yeah, so I think if you take row from R to R, say on the negative axis it is -1 and positive axis it is 1, and you can take gamma is just like gamma is equal to x on R, or say gamma from -1 to 1 means you can take x equal to 1, -1, y equal to 1, and
yeah,
gamma you can take gamma t equal to t, and rho you can take on a negative axis -1 and positive axis in 1. Then
yeah,
for that,
like even though
gamma it is 0.
like
Mhm.
just a minor thing, like we cannot take rho as negative. Rho is always a like a non-negative function. So uh,
Oh, oh, no, I'm saying
yeah,
for
so
the
you
You
can
can make
just
comparison.
say
zero
that
on a
one.
zero row zero on a curve, right?
No. Rho is a function on this metric space X.
No, what I'm saying is you consider two distinct points in the metric space. Suppose that can be connected by a curve, make the function row zero on that curve and one elsewhere, and then you have it, right?
Yeah, exactly. Like I mean, the idea is to make a row in such a way so that two distinct point for two distinct point, this D row is going to be zero. So if you find a curve, okay, if you find a curve like if you find a curve gamma such that L row of gamma is itself zero, then you are done. Infirm is always going to be zero. So yeah, so if rho is zero on a curve, this is going to be zero. Is it fine?
Yep.
Yeah, right.
Yeah. Okay. But anyway, we have a like we don't need to worry that because if rho is positive and continuous, we are always going to have that x d rho is a metric space. Here I will introduce a concept which is known as d rho geodesic. So
Does
rectification.
this infima will exist always if rho is positive and continuous?
Sorry, what?
Is if rho is positive and continuous, this infima exist or not? It
No,
may.
that is no, that we cannot say.
Okay.
Yeah, so that's what I'm going to define. So a rectifiable curve a rectifiable curve in XD is said to be D-rho geodesic. D-rho geodesic if the infimum, so let us say this as a definition one. I mean, equation one. So infimum infimum in one is attained by the curve gamma. Okay. So if if the infimum is attained by some by a curve gamma, we call that curve as D-rho geodesic. So there is a difference between like I mean as a definition there is a difference between a D-rho geodesic and a geodesic in this metric space. Okay, but they are related. That I will come to this point related. So a geodesic in this metric space is nothing but an isometry, and D-rho geodesic is a curve is any curve which gives the infimum. So as a definition there is difference, but like up to a parameterization they are same. So I will come to this point later. Okay, there is one more thing which I want to mention here. But the Okay, so but the discussion on that will be in the extra session when we will talk about the Riemannian manifold as a metric space. So why these metric are called conformal metric? Okay? Why the name conformal? So basically, the thing is uh, to basically know when two Riemannian metric are said to be conformal to each other. Okay, and we will see that. Let us. Okay, so we will see that on a Riemann surface. On a Riemann surface, uh, a conformal metric will always be of the form rho z mod dz. So where rho z is nothing but a positive function, positive continuous function. Okay. So in that sense, these metric are called conformal. I will come to this point in some other lecture. Okay. So up to this, I think everything is clear. Any doubt? We will move ahead. Okay. So now we'll talk about length metric. Okay, yeah, by the way, I should just mention some examples here, like so that it will be clear to, like, whatever kind of examples we see, like examples of metric we see. So like if you take rho z is equals to 1 upon 1 minus mod z square, where z belongs to d. So what is d rho now here? Can you tell me? This is a familiar metric. Anyone?
Is it a Poincare metric?
Yeah, exactly. So this is a Poincare metric on the unit disk. So this d rho is nothing but the we can say that the Poincare disk model of the hyperbolic series. So this is the hyperbolic metric. I will just write. Okay, and you can just do 1 upon imaginary part of z, that will be hyperbolic metric on the upper half plane. Okay, this is also a fairly example to mention, which is rho z is basically 1 upon delta omega z. Okay, so wait. So now let omega be any proper subdomain in Rn. Okay, so we define rho from omega to as rho of, let us say, x. Rho of x is equals to 1 upon this delta omega x, where basically where delta omega x is nothing but distance of x from the boundary of omega. Okay. So so in this case, this d rho is known as the quasi hyperbolic metric. Okay. Yeah, fine. So there are many examples like one can construct with these things. Okay, so we are going to talk about the length metric. So basically every metric space x comma d admits a natural metric called the length metric. Length metric, or this is also known as inner metric. So I said I'm going to talk like we will. Oh, screen is not visible, no?
No.
Yes, it is not visible.
Yeah, just now is it fine now? Is it fine now?
Yes, yes,
Okay.
yes.
Yeah. So write this definition as so let x comma d be uh, rectifiably connected metric space. We define the length metric as, so I will denote it as like lambda x of x comma y is nothing but taking the infimum over all the rectifiable curve gamma and take the length. So this is our length metric. Okay? So where infimum is taken over all rectifiable curves gamma joining x and y. Okay, so and the definition of length space is space. So okay, so if basically d of x comma y is nothing but lambda x of, so I hope the definition is clear. So rectifiably connected metric space is said to be a length space. There are different name of it, like length space, intrinsic space, or a path metric space. If the distance between 2 points is nothing but the infimum of all the curves, infimum of length of all the curves joining x and y. Is it clear?
Yeah.
So I will come to examples of length spaces. So later on, because uh, in a single go, I will mention the examples of length space and geodesic space. So that would be better way to see the examples of length space and geodesic spaces. Okay, so now see we now we have three metric spaces. Okay, x comma d, x comma lambda x, and x comma d rho. Okay, so the first thing is to natural question is what is the topology induced by this lambda x? Topology induced by the length. So observe that this length metric is nothing but when we take rho is equals to 1. That's just a notation that length of the curve is nothing but integral over gamma ds. Okay, so so as we know that since d of x comma y is nothing but ld of gamma, okay, for all x comma y belongs to x, okay, so the identity map the identity map, I mean, identity map from x lambda x to this one, x comma d, is basically one Lipschitz continuous. Okay, so means from one side we have the continuity. Okay? So this means that the topology induced by lambda x is finer than the topology induced by the metric d. Okay, so this means that the topology induced by lambda x is finer than the topology induced by D. Okay, I mean open sets for D are also open sets for lambda x. So is it clear? This is just easy to. But the thing is, this identity map is not a homeomorphism. We have one side, but not the but not from the other side. It is so this lambda x does not induce the same topology. So to mention this remark, so in general, the identity map is not a homeomorphism. You'll see one example, which is a comb kind of domain. Uh, Not a domain, a comb kind of space. So here's one example where we don't have this homeomorphism. So let X be any subset, X be a subset of R2 defined as X is equals to, basically we take 0, 1 interval and basically take a cross product with this one, 1, and union 0 cross 0, 1, okay, with union n greater than equals to 1. What we are doing is we are taking the lines 0, 1. Okay. So it is nothing but, so how do we see this one? So this is nothing but, so yeah. So this is nothing but, so let us say this is 0, 1. So 0, 1 cross 1. So this one. And it will come like kind of closely lines we will be having here. So they are the same length. Okay. So this is kind of a comb kind of domain. Sorry, I'm always saying domain. This is not a domain. This is space. Like we are not taking the interior. We are taking the. So this is a comb. Okay. So now what we are going to do is, so this is all set. Okay. So we need a metric. So equip X with the metric induced from R2. Okay. It's just that metric only. So equip. So X with the metric induced from R2. Whether this example is clear to everyone, like the way we, I mean, the way we have defined the space X, and the metric we are taking just the induced metric from R2. So now consider the sequence. Consider the sequence consider the sequence which is, let us say, n is greater than or equals to 1. So Pn is defined by 1 upon n comma 0. Okay. Okay. So and let p is equals to 0 comma 0. So we have that basically what would be d of pn comma p. So pn comma p is basically going to 0 as n tends to infinity. Okay. Whereas, so what does it mean? Okay, so let me write d Euclidean. D Euclidean of Pn comma P tends to 0 as n tends to infinity. Okay. So what does it mean? Pn converges to P in the metric D Euclidean. Okay. So X is basically with the Euclidean metric. Okay. But but uh, but if we take lambda x of Pn comma P, so wait a minute. So lambda x of Pn comma P is always going to be greater than or equals to 2 for all n. Why is that so? Can you tell me?
First, it will go above to
Yeah, exactly.
say no, and then come back. We
Yeah,
have at
exactly.
least two length.
Yeah. So first is it. So first, okay. Let me. So first, it is kind of it. It has to cross this line, then again come back to this one. Okay. So this is kind of covering twice. So it is greater than or equals to 2. So means this does not converges in this metric, isn't it? Pn does not converges to P in the metric lambda x. What does it mean? It means that thus the identity map, okay, from x to d, x comma d to x comma lambda x is not continuous. Is not is not continuous. Okay. So I hope it is clear. Okay, fine. So this is about the topology. But yeah, but okay, I will mention this result later. But it is important to know when this identity map is when this identity map is homeomorphism. I will mention two reasons for that one. Why is it important to know that this this should be a homeomorphism? Like, sorry, when this is a homeomorphism. Uh, but for that one, I need to mention some results, which is related to the inner metric. Okay, uh, so some results. So there is like it is a natural question which I will write now. So like observe that if gamma ab to x is a curve, if gamma is a curve in x comma lambda x. Okay, so gamma is a function from any function from ab to x, and it is continuous in this metric x comma lambda x. Okay, then gamma is also a curve in x comma d, isn't it? Is it this should be clear because of the continuity from one side, because from here to here it is continuous, the identity map. Okay, so if we have a curve here, that curve will be continuous here also. If a function is continuous from this in this metric space, then it will be continuous in this metric space. Is it is it clear?
Yeah.
Okay. But what about the converse? Because like if a function, like if we have a curve in xd, can we say that that is also a curve in x comma lambda x? Okay,
I think no,
that is a
we can take the same example. Com.
which
Means
example?
the converse may not be true, I'm saying. Means the same com example or take some gamma curve. I don't know.
Yeah, I mean, but the kind of gamma we are taking, it's again a curve in this one also.
Yeah.
Yeah,
Oh,
so we are talking about the curve. Actually, the converse is also true under the
oh,
rectifiability assumption.
yes.
So, I just asked because like it seems that because from this side to this side continuity is not there, so it might be the
Yeah,
case that
means,
gamma is, yeah.
right. Means the topology is not same. So yeah.
Yeah, exactly. So might be that we can find a curve which is continuous, which is a curve in xd but not in x comma lambda x. But the converse is like it is true under the rectifiability assumption. So
Uh,
the converse, I will mention that one. The converse is true under the rectifiability assumption. What does it mean? It means that, let me mention now. So let us say this one is proposition. Like, so let gamma such that a comma b to xd be a rectifiable curve. Uh, then then gamma such that a comma b to x comma lambda x is continuous. Continuous. That is, gamma is also a curve in x comma lambda x in this metric space. Okay. So like the idea is fairly simple. Is like, okay, let me just mention a proof. Okay, so it's like, so for all, okay, let me, okay, so let for all t naught and t in a comma b, okay, we have, by the additivity of length, we will have lambda x of gamma t naught gamma t is less than equals to basically LD of gamma t naught comma t, which will be the, this will be the difference. So this from here to here there is some calculations one has to do. I will just mention and that will be there in the notes when I will upload it. So t comma t minus the LD of gamma t comma t naught. So once we take t tends to t naught, this is going to be 0. And okay, I think I forgot to mention one result in the earlier lecture uh, regarding the continue, like the limit of the length. That I forgot to mention. Okay, I will mention in the notes when I upload it. We, so we have to use one result here, which I forgot to mention earlier. But anyway, this that result will give that as t goes to t naught, this is going to be 0. So lambda x of gamma t naught gamma t, this is going to be 0 as t tends to t. Okay, so okay, we are fairly good here that if we have a curve in xd, rectifiable curve in xd, that is also going to be a curve in x comma lambda x. But what about the length of that curve? In fact, the length is going to be same. So that is quite good. That the next proposition says that let says that e comma v to xd be a rectifiable curve. Then what we have is that LD of gamma is nothing but L lambda x of gamma. Means the length of the curve, what does it mean? This means that length of the curve gamma in a metric space lambda x. These are going to be same. And one corollary of this result would be what? Can you tell me? One corollary would be that, okay, uh, this x comma lambda x is a length space. Okay. So I hope it is clear now. I mean, this is quite easy to prove. There's like, I should left the size only. You just have to take the variation with respect to a partition of DL. Then you'll just put the inequality that a lambda x between any 2 points is nothing but less than equals to the length of the curve joining those 2 points. Then you will get the inequality. Okay, so is it clear? Up to this point, everything is clear now?
Yeah.
Okay, so, okay, as I said, it is important to know that when this identity map is a homeomorphism, uh, the question is why. So I'm going to mention those things, but before that, let me just mention a notation which I will use. So for any two metric d1 and d2 on x, okay, we write d1 is equivalent to d2 if they induce the same topology. They induce the same topology means identity map is a homeomorphism. Topology. Okay, so now at this stage we have three metric spaces, which is x comma d. Once we have a row function like density function x comma d row. Okay. So related to these things, I will mention some results. Is the result one will be like, so lambda x and this d row, these are always, they always induce the same topology. Okay, lambda x and d row. What does it mean? In particular, I will mention a reference where one can find the proof. In particular, d is basically equivalent to lambda x if and only if d is 0. Okay, so result 2 is uh, so length of the curve gamma is less than infinity if and only if L d row of gamma is less than infinity. Okay, so remember that we also have different notion of we also have different different length for a curve like LD of gamma, L rho of gamma, L d rho of gamma, sorry, L d rho of gamma, and L lambda x of gamma. So these two are equivalent, we have seen. Okay, there's no problem. And we say that, result 2 says that this is rectifiable if and only if this is rectifiable. Okay, so a curve in metric space xd is rectifiable if and only if that curve is also rectifiable in metric space d rho. So rectifiability is so rectifiability of a curve is independent of the chosen metric d rho. Okay, whatever the rho you take, a continuous and positive function which induces the metric, whatever the density you take, rectifiability will not be a problem. Result 3 is important, which is related to the uh, result 3 says that if this length of gamma is finite, if gamma is a rectifiable curve in the metric space x comma d, then what we have is L d rho of gamma is always less than or equals to L rho of. So now we have a relation between this and this also. That L d rho of gamma is always less than or equals to L rho of gamma. Okay. So now, as I mentioned, why is it important to know that the identity map should be homeomorphism? I'm going to give the reason for that. So reason 1 is, you can also write it as theorem. It says that if the identity map x comma lambda x is the identity map x comma d is homeomorphism, then this is quite a nice result. L d rho. So L d rho of gamma is nothing but L rho of gamma. Okay. So this is quite a nice property to have, that the identity map is a homeomorphism. It basically gives that the equality holds in this inequality. Okay. Is it fine now?
This is true for all row.
Yeah, this is true for all row. It doesn't
Okay.
matter. Yeah. The proof of this, that's why I mentioned it as a theorem, because the proof is a bit of lengthy. Sorry, I should say a bit of technical, but I will mention the reference for the proof once I upload the notes. Okay, this is one reason why we want this identity map to be a homeomorphism, and I will also mention another reason. So one more reason I will mention, but before that, let me. Okay, so now what does this gives? What does this theorem gives? We have a corollary. It is now. This says that x d rho is a length space. Isn't it? I hope this is clear. Because what we're having is d rho of x comma y, which is nothing but the infimum of L rho of gamma, okay, over the gamma, which is nothing but infimum of L rho is nothing but L d rho of gamma, okay, and this is nothing but what is this? This is nothing but lambda x of x comma y, isn't it? For this metric D rho. Is it clear?
Yeah.
Okay, so one can ask what are the conditions that this is going like what are the results which guarantee that this identity map is a homeomorphism. So let me just mention that one again. uh, some sufficient conditions. uh, if uh, if x comma d is locally quasi-convex. So what do you mean by convex? Sorry. So this is locally quasi-convex. Basically, let me just write. So metric space x comma d is said to be quasi-convex. Quasi-convex if uh, if if there exists a constant c, and let us say if there exists a constant c such that d of wait a minute. So length of the curve gamma is less than equals to c into distance between these two points, where gamma is where gamma is a curve, it's a rectifiable curve. Rectifiable curve joining x and y. Okay. Okay. And this basically gives us that. Yes. Any question? Any doubt? So
No, please carry on.
okay. So what we have is now omega. Let us take a domain omega subset of Rn. Okay. Domain. Then
Abhishek,
uh,
so I think
yes.
Sanjay asked in chat what should be definition of convex.
Sorry, what? Wait.
Sanjay asked in chat, you can look at it.
Okay, just wait a minute. I have to. Can you just read the question?
Or yeah, what should be definition of convex? Or
Convex is
why convexity is coming in, means why the name is quasi-convex, I think he's asking.
okay. So like okay. So it is like suppose if the domain is convex, suppose the space is convex, we are always going to have a straight line joining x and y. Okay, and the length of that straight line is nothing but modulus of x minus y. So every convex is nothing but one quasi-convex, isn't it? Is it clear, Sanjay? So this is
He said
basically a
okay.
generalization of convex. Like in a convex domain, if we take any 2 points x and y, we have a straight line joining these two, and length of this straight line, let us say gamma, length of this curve is always going to be x minus y, okay? Which is nothing but let us say d of x comma y in the Euclidean space. Now we are generalizing this concept to uh, to uh, to in general metric spaces, and we are making this constant. Okay, yeah. So C is greater than equals to 1 here, and we are making this constant C, and like we are generalizing the concept of convex to in the general metric space setting.
And is the C will depend on gamma?
Sorry.
Is C will depend on gamma?
No, C is like it
Uh,
depends. Like it's a universal constant. Yeah. Is it clear?
yeah, I said okay.
Okay. Okay. So where were we? Uh,
Okay, he said if one gamma works, then what about other gamma?
sorry.
Means you have given for one gamma, right? So there may be many gammas which go from X to Y, right? Say in a convex domain,
Uh-huh.
you have just a straight line, but you can have a many gamma which may loop around and go to Y. Then maybe the length maybe blow up, at least for this example. Means I'm saying
Okay.
dxy is finite and c is finite. So you may take gamma such that like the length of gamma
Oh,
may be
okay.
infinite.
Oh, so sorry. Okay, wait. I think I have in the definition. I should be more precise in the writing the definition. So it's a quasi-convex if there exists a constant c such that every x comma y in X can be joined by a rectifiable curve gamma. So where gamma is a rectifiable curve joining X and Y, so can be joined by a gamma. Sorry for the this. I just wrote that gamma is a rectifiable curve joining XY, but that is basically can be joined by a curve. Okay. Now I think
Oh,
the
okay, means
answer to
one
this
curve.
question is clear. So for a convex domain, we have a straight line at the place of gamma. That's
Oh, okay,
like
okay. So this is just
that's what
for
I was.
one gamma,
Yeah, exactly.
not
That's
for
what I was
okay.
going to convey.
Uh-huh.
Yeah.
Okay.
Is it fine now?
Yeah,
So
now
this
it
is
makes sense.
yeah. So a metric space XD is said to be quasi-convex. So there exists a constant C such that for every x comma such that every x comma y can be joined by a curve. Every x comma y can be joined by a curve, a rectifiable curve, which satisfies this thing. Fine. So and locally quasi-convex means you take a point in a neighborhood. It is quasi-convex. So this is a result which says that if omega is a domain, then this then identity. Okay, so omega is a domain, then identity map omega comma lambda x to omega comma d Euclidean is a homeomorphism. Okay. So yeah, fine. So this is a good. So this is one such good result that okay, if you take a domain in Rn, we are fine. We don't need to worry about the like we don't need to worry about the homeomorphism. It is always going to be okay. So I will move towards the what we are geodesic. So basically, a curve gamma such that a comma b to x is said to be geodesic. Geodesic if it is an isometry. That is okay. Yeah, anyway, isometry is clear. So that is d of gamma t gamma t dash is nothing but mod of t minus t dash. for every s belongs to A comma B. Okay, and we say that a geodesic space so a geodesic space is nothing but so XD is said to be geodesic or in like geodesic space or in short geodesic if every pair of points pair of points x comma y can be joined by a geodesic. Okay, so now here I'm going to mention an important result which is by Hoff and Rhino. Hoff-Rhino theorem. Okay, so let x comma d be a length space. So this is important that we are already assuming that it is a length space. Then following holds. Following holds. So first thing is if x comma d is complete is a complete metric space, complete and locally compact. Locally compact. So locally compact means at every point we have a neighborhood whose closure is compact. Means every point contains means every point has a compact neighborhood. Then it is proper. And proper means uh, so basically the proper means that every closed ball is compact in that space. So basically properness implies the locally compactness. Once you have that every closed ball is compact, that is going to work as a compact neighborhood for the point. Like any one ball, any particular ball. Okay. So yeah, so if a metric space is complete and locally compact, then it is a space. This is the first one. Second one is if XD is proper, then it is geodesic. Geodesic space. And the third one is if XD is locally compact. If XD is locally compact, then so we already have an assumption of length space. If in addition we have a compact locally compactness assumption on the XD, then it is proper if and only if it is complete. Okay. So this is the different versions of Hop Rhino. Yeah. So any doubt up to this point? Okay. So I am going to mention some properties of two properties of geodesic, and then I will mention reason two why is it important. So let me first write a reason of that. Like first, let me write the reason why homeomorphism is important. So reason two. Okay, so this I will note it as theorem. So let x comma d be a rectifiably connected connected metric space and row such that x comma d to 0 comma infinity be continuous. Okay. Suppose suppose that suppose that suppose that the identity identity map omega comma lambda sorry identity map x comma lambda x to x comma d is homeomorphism, then following are equivalent. Following are equivalent. First thing is x comma d row is a geodesic space. Second is for each x comma y belonging to x, d row geodesic exists. So as I said earlier, d row geodesic and being x comma d row a metric space, those are equivalent. Okay? Once we have this identity map is a homeomorph. So what I mean that, see, we are saying that x d rho is a geodesic space. It means that any 2 points can be joined by an curve, which is an isometry. Okay, so gamma is an isometry x d rho. Okay, so this is an isometry. That's what we mean by a geodesic space. But by the second point, what do we mean? We are saying that there exists a curve which gives the infimum. So basically, this L rho of gamma is nothing but d rho of x comma y. Okay. So this can be any curve. That gamma, this can be any curve without being an isometry. Okay. But what what we will do, we will parameterize this curve gamma with respect to the arc length. This is going to be the isometry. So as I said earlier, that the curve which gives the geodesic, like I mean, the curve which like okay. So for x comma d rho to be geodesic space, we need a geodesic gamma. Okay, and for d rho geodesic exist, we need a curve. Let us say sigma. Let me write sigma. So these two curves can be a different curves, but once we parameterize with respect to arc length, the curve is going to be an isometry. So we don't have any problem with that thing. Is it clear? I will mention the properties of geodesics. Just I don't think I would be able to prove that one. But anyway, it will be there in the notes. So let me just mention two properties of the geodesic. From using those two properties, this can be proved. So I will write as an exercise. Exercises. Prove theorem 2 using property 1 and property 2. Okay, so I'm going to mention these properties now. So property 1, this is fairly easy to prove. So let x comma d be a metric space, and let gamma such that a comma b to x be a geodesic, then this gamma is basically parameterized by arc length. So that is nice. So gamma is parameterized by, just use the definition and it will be fairly easy to see, parameterized by arc length. Okay, so this is one such property, and the property 2 is property 2 regarding the converse. When can we say that a curve which is parameterized by arc length is going to be geodesic? Okay. So I think Ravi asked earlier once we are discussing that the curve parameterized by arc length, can it be a geodesic? Ravi?
Yes.
So this will be, so this result will be regarding to that one only. So
Uh,
let gamma such that AB to X be a curve which is already parameterized by arc length. Parameterized by arc length. Then following are equivalent. First thing is gamma is a geodesic. Second thing is for every real number u and v, they are basically a is less than u is less than v is less than b. We have d of gamma of a comma gamma of v is nothing but d of gamma of a comma gamma of u plus d of gamma of u comma gamma of v. Okay, and the third is basically the length of the curve gamma is nothing but the distance between the endpoints. Okay? So if a curve is already parameterized by arc length of the curve being equal to the distance between the endpoints is same as that curve is geodesic. So we need only this condition to check this one. So if curve is already parameterized arc length, and if that condition this condition holds, it means that curve is a geodesic. So these are two properties. Using these two properties, one can prove this theorem too. So yeah, one can just take the arc length parameterization of the curve, and one will arrive that these two conditions are equivalent. Okay, so I will stop here. Any question?
yeah, so so I don't know it's relevant or not. So for a domain in Rn, you said its length is space. So for a domain in Rn, does the geodesic always exist?
Sorry, what you said?
I'm saying for a domain in Rn, is the geodesic will always exist or
Okay,
any row?
once we talk about geodesic, we also talk about
Mhm.
a metric space
Okay,
so that
yeah.
we can check
So
the isometry. So what is
right,
your metric on the domain in
it
Rn?
may be quasi conformal metric or whatever.
Yeah, means yeah, quasi. Yeah. So again, so for this question, we need to fix a metric.
Mhm.
Uh,
Uh,
Quasi hyperbolic metric, or
yeah,
for a
quasi hyperbolic.
planar. Yeah. So for quasi hyperbolic metric, the geodesic always exists.
Okay. Then I think the okay next question is it visible with respect to that one?
Okay. Not every domain is visible with
I
respect to that metric.
okay.
Means so yeah.
So which
So
kind of
the condition.
domain?
Yes.
Yeah, which kind of domain may be visible with respect to this metric?
It is kind of
Because
with respect to quasi hyperbolic metric.
yeah,
Yeah, so it is kind of domains which are uniform domains. So for
I see.
uniform domains, we have so geodesic. So this condition we have that uniform domains are quasi-convex domains. Plus we
Mhm.
have cone arc condition on the between any 2 points there exists a curve which satisfies a
I,
certain cone arc condition.
I
So
see.
these kind
So,
of domains are
uh,
visible.
so is there a necessary and sufficient condition of a domain with visibility and means we
No,
can have some
no.
I-
There is no such sufficient condition neither in this setting nor in the Kobayashi setting at present.
right. Okay.
I mean, I mean a good, necessary, and sufficient geometric condition that is
Right.
not there.
Okay.
I mean, I
Mhm.
will talk about visibility in some other sense once I will talk about the Gromov hyperbolicity.
Yes. Thank you.
Yeah. Any other question?
What are the references you are following?
References I think I have mentioned in so this is wait a minute. So there's a book by Popendus, Convexity, Metric Space, and Non-Positive Curvature.
Okay.
So that one can use. I think it is there in the cover page of my first lecture references.
Okay.
First lecture note. It is there on the cover page.
Okay. Fine. Thank you.